Hi, everyone. Thank you for joining this talk on Fuzzing Hyper-V, Microsoft Hypervisor. I'm going to start with a few words, introduce myself, a few more words, because you know the most important part, obviously. So I'm a security engineer. I work at Google. I'm passionate about vulnerability research on low-level layers, systems. Also, I'm an active member of women in security networks, like blackhoodie.re, like note for the women in the room. And the research project that I'm going to present was done as a 20-person project with Project Zero. So a 20% at Google is the opportunity we have to spend up to 20% of our time on the project of our choice, other than our primary projects. So the first question you may wonder is, as a Googler, why choose Hyper-V? That might sound a little bit counterintuitive. So first, it is aligned with Project Zero mission. Beyond that, also Hyper-V is a key target for security researchers because it is the hypervisor running Azure, Microsoft Cloud, and it's also running on all the modern version of Windows because of the feature of virtualization-based security. It can run on modern versions of Windows. So any zero-day may have a huge impact. And that's why it's a particularly interesting target for researchers. Beyond that, at a personal level, virtualization is particularly fun because it covers several layers. It's endless, an endless topic, so really fun to work on that. Like, yeah, nice playground. So the goals of the research was to find vulnerabilities on Hyper-V, report them to Microsoft. And the strategy to do so was to instrument Hyper-V for vulnerability research. And to do so, a Fuzzer was written. It's called Hyntrospect. Here is the link. It's open source. In a few words, it's covering part of Hyper-V. The approach that was taken is very pragmatic. I'm going to explain why, because there are a few constraints also that I had to work around. So first, I'm going to cover some background on Hyper-V. Then I'm going to talk about the research target that I chose, the Fuzzer itself, and then I will present the results and eventually the future endeavors. OK, so first, some background. I want everybody to be on the same page to start with. So let's get started with what Hyper-V looks like. Yeah, I'm not going to explain everything. Don't worry. Let's get to the most essential part. So to start with, Hyper-V is a hypervisor, type 1 hypervisor, which means it's the equivalent of an operating system running directly on hardware to run several virtual machines or VMs and virtualized environments. So here, the hypervisor is there on the stack. And Hyper-V has a specific structure. It differs from other hypervisors because it has a privileged VM, which is called the root partition. And the virtualization is not only implemented in the hypervisor, but also in the root partition. And as opposed to that, we talk about children partitions, which are regular virtual machines or VMs. And by the way, in that talk, I'm going to talk about VMs. When I talk to VMs, I refer to children partitions. And something that is really important to note is the Vmworker process, because it will be helpful later. So this is a process in the userland of the root partition, which is part of the virtualization stack. And every time a child partition starts, a Vmworker process is created. So it kind of holds the VM in a way. So I hope I didn't lose everybody. I said I wouldn't detail everything. So what I was looking for was a familiar attack called guest-to-host escape. So the idea is to gain code execution from a virtual machine into the hypervisor. So the perspective taken is the one of an attacker, Azure attacker. So let's say you create a VM on Azure, you are in the child partition, and you want to get back to the hypervisor to get code execution in the hypervisor, because it's interesting, because lots of things happen there. So you may be interested in different layers because of the architecture of Hyper-V. You may be interested in the hypervisor, but you may be interested also in the root partition kernel, the root partition userland. So all those are interesting. So this is what I was looking for. Also, on Hyper-V, there are other types of attacks that are interesting, like, for example, leaking information from the hypervisor is interesting, but also denial of service on the hypervisor as a note. I'm not going to consider VM to VM, for example. So let's zoom out. The attack surface on hypervisors is pretty large, and this is a slide I've taken from Alissa Essage at Zerocon 2020, because I think it self-explains everything that was added. So let's go back to what I was saying. A hypervisor is some software that is added on, directly on hardware, which means lots of software added and lots of things to deal with. So also very complex code and large attack surface. So we could, for example, speak about the hypercall handlers that are handling the communication with the hypervisor. Also the peripherals, graphics, networking. I mean, lots of software is added when implementing a hypervisor. And indeed, that translates, as it is complex, into lots of CVEs. So this is not only for Hyper-V, by the way. This is for lots of different hypervisors. Hyper-V also had some CVEs. So you can see that it's complex code worth investigating. So this is about the motivation. And if we zoom in and talk about Hyper-V again, because of its architecture, we can consider different attack surfaces. So in the root partition, but also in the hypervisor itself, all those are interesting. So this is not exhaustive. I'm not going to get into details. You can find more things on first steps in Hyper-V research. And also, it depends on the VM generation. It varies a bit. So there was lots of research already done. I'm not the first one looking into that, obviously. First, Microsoft and MSRC is a very active contributor for the community, and I think it's a good time, as it is BlueHat, to say thank you, Microsoft, for that. So there were several blog posts, for example, first steps in Hyper-V research that really help researchers get started on Hyper-V. Also, there are some posts on Hyper-V components, on MSDN, talks on vulnerability found internally. There have been lots of talks at BlueHat USA these past years. And eventually, Microsoft makes our life a bit easier because there are symbols for some of the key components. Not all the components, like note for Microsoft, but not all the components, but some of the key components, and also, well, debug strings in the code, but I'm going back to that a bit later. And there are also quite some external contributors. The community is quite active, so I want to mention a few, like Gerard, for example, who has the dedicated blog post, GitHub, and quotes several researchers on that one, Alissa Essage, but also Ophir Arpaz and Peleg Hadar, who presented last year at BlueHat USA on a different fuzzer, targeting a different layer. Great talk. So now that you can see a bit more the attack surface, the question is what to target and why, because the research target is quite, the attack surface is quite large, so where to start? And I chose to focus on the emulated devices controllers, so I'm going to explain what it is to start with. Let's start with something simple, regular Windows without hypervisors. That Windows may want to write to disk or may want to access some resources, peripherals, and it will talk directly to almost directly, let's make it simple, to the device's controllers. But when there are several VMs want, there's competing access to the resources. So in some way, the hypervisor needs to deal with that. And one way is to give direct access from the VM to the hardware controllers, which is called pass-through. And there are two other techniques, emulation and paravirtualization. I'm going to talk about emulation. So with emulation, what happens is the hypervisor acts as a proxy. And the guest is unmodified. It sends requests to the hypervisor. The hypervisor then deals with it as if it was the controller. So it either sends it to the real controller, or it aborts, or it handles it software-wise. So you can imagine that there's lots of code added to do that, and it's complex. In Microsoft, they are called virtual devices or VDEVs. And concretely on Hyper-V, this is what it looks like. So coming back to the root partition, child partition, the devices are implemented in DLLs that are loaded by the Vmworker process, so in the userland of the root partition. This is true only for generation 1 VMs. So if you're not familiar with that, there are two generations. Generation 1 is more legacy. Generation 2 has more modern features. So when I started this research, Azure was mostly running generation 1. I assume it's moving a bit because of Windows 11. I don't know the status right now, but it seems to be still widely used. And some examples of those devices are PS2, or floppy, or IDE also. All those are emulated devices in generation 1 VMs. So now, coming back to the question, why choose the emulated devices? First, they are complex. Usually there are state machines, for example, with status registers, different updates, conditional commands, so it's quickly very complicated. It's an area that has been proven to be prone to bugs in the past for several hypervisors, including Hyper-V. And also, as I was saying, Azure still uses generation 1 VMs, so it's still an interesting target. Hyper-V is developed in C++, which leaves room for memory corruption bugs. And finally, as they are living in some way in the userland of the root partition, it leaves room for potential guest-to-root partition escapes. So all that makes it an interesting target. So if we look at what the requests look like, coming back to my request to my disk, so the VM issues a request to a disk as if it was a real disk talking to a real controller, which manifests in I/O ports, I/O commands. So these are CPU instructions sent from the kernel of the guest, in EX, DX, for example, out DX, EX, like DX is the port, EX is the value. You can read more about that in the Intel manuals if you're interested. So these are Intel instructions. And those instructions are sent. The hypervisor intercepts it, intercept them, then redirect them through the vid with callbacks, and eventually it lands in the userland of the root partition. So this is a simplified view, though. It works for some of them. It doesn't work for all of them. Some VDEVs are a bit more complex with MMIO handling, also with some VM bus communication. So the VM bus is an inter-VM communication channel, but I'm not going to get into details with that. I'm going to stick to the IOs. And if you want to read more, there's a good blog post attacking the Vmworker process. So the starting point for me, now that we know that the code is in DLLs loaded by the worker process, this is the starting point to get to know what's going on. We want to look at those in-out instructions, where they are issued, what's going on, and the flow, and eventually what's going on in those DLLs to handle those instructions. So the first step is to reverse those DLLs and to find the handlers that hold all the information, so the IO port, the length, and the value when it applies. This is an example, the VM emulated storage.dll, for example. And actually, for all the devices, there are two entry points that are always implemented, which are notify IO port read and notify IO port write. And we can see the ports, length, value there. So that's exactly what we want to look at. So on the plus side, there are the symbols that are available for those DLLs. There's no particular difficulty. There are even some debug strings. So great. Well, on the not so good side, it's C++ with indirect calls, but nothing specific, like just C++. So now we know where to start. The question is, what do we want to do with that? Because we know where it's implemented. We can see what's going on, although, as I was saying, it's very complex code. So there are different strategies from there. One strategy is to look at vulnerabilities manually, look at the different devices, check for error logics, for example. Another approach, as it is complex code, is to write fuzzers, and that's the one I took. And the inspiration for me came from different factors. So first, I was working on some open source code, and I used libFuzzer, which is a fuzzer for open source. And that was extremely efficient because it's using a coverage-guided technique approach. So coverage-guided fuzzing is the fact that the coverage is tracked on the target. So the code that is executed is tracked. And the input that increases that coverage is deemed interesting and helps creating more interesting input for the future. So you can see that it's a positive loop, and it helps covering more code. So I found the technique very efficient, and I was wondering how to do that, knowing that in that case, the problem is that the binaries are not open source. More complicated. Also, Microsoft published on their coverage 3 years ago at BlueHat IL, and this is a slide from that presentation, a case study, and I was wondering how to get back to that result from an external perspective. And finally, the last source of inspiration was a blog post on CV published in 2018 about IDE and the bug that was found on IDE. So my question was, I would like to do the same. I'm not working at Microsoft. I don't have the sources. How can I do the same closed source? And to do that, there are some existing tools already for Windows. So just to summarize, we are in userland without the sources. And to gather the coverage, for example, we can talk about DynamoRio, we can talk about Intel Pin, Mesos, TinyInst. There are some options. Also for fuzzing, WinAFR with DynamoRio, Jackalope, to quote some of them. For memory corruption detection, this is important because this is C++, so we want to catch memory corruption errors. And when we have the source code, it's much easier because we can use address sanitizer, ASAN. Now it's not the same, but good news, page heap with JFlags helps doing that. So there are plenty of tools, and the question is, why create yet another tool? That's because of the different constraints of the environment. So I'm going to give you more details about those constraints. First, the target is a DLL. It's not an executable, which discards some of the fuzzers that do not apply to DLLs. Second, a very common technique when fuzzing is to extract the code that is deemed interesting, to emulate it and deal with the side effects and context, which means recreating a context that works. But here we are speaking about virtualization, VM states, so it's quite heavy. So that's why I didn't go for that approach, because it seemed quite a heavy approach. Also, some fuzzers require starting the target with the instrumentation. Well, let's rewind. I was saying the Vmworker process starts when VM starts, which means that if you want to start instrumentation on the Vmworker process, it will make your VM restart, which is not too desirable because starting a VM is quite slow. Also, the runtime operations are very specific, injecting IOs. Something also I want to talk about. When I started developing, some tools did not exist at that time, and I'm thinking about Jackalope, for example, developed by Project Zero. And that's also possible for future optimizations to modify the implementation to include those. That could be helpful. And something I added to myself as a constraint was to use a minimal set of programming languages because I wanted it to be easy to maintain in the future. So added constraint. And eventually, I wanted the fuzzer to be portable to other cases, so portable to other cases in the userland of the root partition. So I wanted something generic enough. So I restricted the scope to Windows guest VMs, Intel CPUs, not ARM, Generation 1 VMs, and binaries in the userland of the root partition, to summarize everything. And yeah. There you go. So the design choices were emulation versus execution. As I was saying, I went for execution. So I decided to run a real VM and to run it inside the debugger, which is called debug shell, which is a wrapper around Windows debugging engine. So real runtime. For the coverage, I use a technique. I'm going to get more details about that, to give more details about that later. The int3 technique described by Samuel Gross for TrapFuzz and Brandon Falk for Mesos. For the memory corruption detection, I used page heap. It was already there, handy. And the type of bugs that can be found are memory corruption bugs, state machine logic errors, possibly use after free. It depends if I get a blue screen or not. Race conditions are off the table because the fuzzer is not multi-threaded, so no, that's not going something that will be caught. Also, something that is extremely important when fuzzing is to come back to a reference state. So we want to come back to a clean state for every fuzzing loop. And that's extremely important because worst case, you modify your VM, lots of things happen, you get a crash, and you cannot reproduce it because of everything that happened before that you cannot trace. And that's very sad. You don't want that. So the idea was to come back to a clean environment. So every time a new fuzzer input was processed, it would start on a new environment. And this was done using Hyper-V checkpoints, which are the equivalent of snapshots for other hypervisors. So to be clear, coming back to a clean VM image before every loop. The mutation strategy chosen was custom. The language was PowerShell, which may sound funny for a fuzzer because PowerShell is a scripting language, and scripting means slow. But the big plus of PowerShell is that it integrates very well in Windows. It's done for that. So it enables interacting with lots of APIs on Windows, like, for example, sending commands to a VM, interacting with Hyper-V Manager. So very handy. And as I was saying, the idea was to minimize the work and reuse as much as possible existing tools. So that's why I use debug shell, the debugger, chipsec, in the guest VM to send the IOs. So chipsec is a utility that does lots of things for UEFI and so on, but here the idea was to leverage sending IO ports and their drivers. Page heap optionally, and Lighthouse and IDA optionally also to visualize the coverage and to to prepare a list of breakpoints. Coming back to that a bit later. And this is what Hyntrospect looks like. So the fuzzer runs at the same level as the debugger and the target. So it starts the debugger, which attaches to the Vmworker process that loads the DLL. Has already loaded the DLL actually when it's attached. At the same time, the fuzzer injects commands in the VM to chipsec in userland. Chipsec communicates with its driver in kernel that sends the IOs. Then they are sent to the hypervisor and redirected to the userland of dual partition. Also, the fuzzer monitors the VM. So that's how everything is together, works together. One more note, you can run it like that, but usually I run it nested. This is much easier to come back to something and, to deal with everything and make sure that if I get a hypervisor crash, it will be contained also. So the workflow is as follows. First, the user, and that's the only mandatory input, needs to prepare a config.json file with some minimal data like the VM name, checkpoint name, VM username, password, IO ports, those kind of details. Also, if possible, it's encouraged blocks addresses. I'm coming back to that later. And then the main can be started. If the arguments are valid, the fuzzer master starts. Then it starts the input generator, which prepares some file for the fuzzer to work on. Then it starts the debugger, which attaches to the Vmworker process that holds the VM, and eventually a monitoring process is started. So this is what it looks like in the end. I'm going to get more details, into more details on some of those aspects. So first, coverage collection. This is important for a coverage-guided fuzzer, obviously. So I'm using block coverage. So it means that if you disassemble a DLL, for example, with IDA, Ghidra, it will be disassembled in blocks. And the idea is to take the addresses of those blocks, put them in a list. And here, A and D have already been executed, so they are no longer in the list. B and C have not been executed, so they are still in the list. B gets executed, it's removed from the list. Then C gets executed, it's removed from the list. You get the idea. And this differs from, as a note, edge coverage. Edge coverage can be better in some aspects, harder to implement, so it's a choice. And also, I'm not using counters, so either the block is executed or it's not executed. Could be an option also later to modify the fuzzer. And the int3 techniques. So what is an int3 first? An int3 is actually a software breakpoint used by the debuggers. So it's an interrupt. And that's where debug shell comes into play. Because at the beginning of each block that has not been executed, an int3 is set by the debugger. Then once the execution gets there, the debugger is notified, removes the int3, does whatever needs to be done about the input, because at this point it means the input is interesting because it enabled extending the coverage, and then resumes execution later with the regular code. One note also, at the beginning there are plenty of addresses in the file, so it's pretty slow because the debugger needs to stop for every new block that is executed. Over time it becomes faster and faster because there are less and less blocks that have not been executed, and those are the most interesting ones, actually, usually. One more aspect which is very important when fuzzing is the generation of the input files. So to be clear, the input files here are I/O operations that are encoded. So first, it's very encouraged to record seeds, and there are helpers for that. I'm not going to talk about helpers because we won't have time, but there are different helpers. One is to help generate seeds of legitimate traffic. There are two types of files that are considered for the fuzzer: the corpus files, which are permanent residents that are deemed interesting, and input files that will be tested. And every time there's a coverage increase, the input file that is being processed is kept aside, truncated at the latest change, and kept aside, put in the corpus. And there are three strategies to create new input files: mutation, append, and random generation to cover new cases also and give more opportunities to cover something completely different. So the format is as follows. First in-out operation, then decide on the port with the second byte, then the length, and if it applies, a value is read, given the length, and so on and so forth in the file. Something also that is critical when fuzzing and building a fuzzer is to think about crash detection, because you want to catch them all, you don't want to miss some crashes. So it happens at two levels here. First at the debugger level, because if the debugger receives a fault or interrupt that is not an int3 that it's supposed to receive, there's a problem. So the debugger will create a crash folder with all the artifacts that are required, and there's also a monitoring process that is started by the debugger just in case, second level, and it tracks the VM uptime, because it does some polling, and if in between the VM uptime goes down, it means the VM has restarted, basically. So the crash folder is composed of logs, event logs, everything, and everything needed to replay also the case. So this is how the fuzzer is built, and optionally, it's possible to visualize the coverage in IDA, also with Lighthouse. So now you've seen all the components to make the fuzzer. So you have an idea of how it works. You got most of the details, and this is what it looks like in practice. So I know it's small, but I'm going to explain quickly. Top right-hand corner, this is the main console. Top left-hand corner, debug shell. Most of the other windows are hidden, and these are folders with the different artifacts, Hyntrospect, and input files. So this is what it may look like on your own computer. So now let's dive into the results of the fuzzer. So first, the fuzzer was only run locally for now. It was run on 4 devices, i8042, PS2, video S3, floppy, and IDE. The local setup was a dedicated workstation, 32 gigs of RAM. I'm just sharing that. It's a bit boring details, I guess, but just in case you want to reproduce that, it's possible to do that with, well, a dedicated workstation at home. And also, the first thing I noticed is speed limitation, and I would say that's the main bottleneck. And it's not tied to restoring a checkpoint, actually. It's tied to setting breakpoints in the debugger. and it's not something linear. So if you want to set 150 breakpoints, it takes less than a second, super easy. 500, 6 seconds, and so on. So that's why also you want to be very focused when you set your breakpoints at the beginning. The next goal is to port the fuzzers to clouds, so GCP or Azure, to get more runs and get more wider results. So after 3 days of run locally, the coverage is about 40% for the devices, which may sound low, but actually you need to remember that the start, init, and stop functions are never called because we are attaching to a running VM. And the debug strings blocks are skipped. And actually, if we consider all the functions that at runtime, most of them are covered. Like almost all of them were covered. So the coverage doesn't look that high, but it's actually pretty high in terms of runtime functions covered. One result I got, but it was a bit of a roller coaster for me, I'm sharing the roller coaster with you, was a guest VM crash found. So it was on i8042 device, reproducible all the time, consistently. And you may wonder at this point, why are we talking about a guest VM crash? Because there are so many ways to crash a VM, actually, when we are administrator of the VM, right? Well, in that case, it was still interesting. It still caught my attention because there was a blue screen consistently, but with different error messages every time. So I was getting error messages like PFN is corrupt, for example, or attempted write to read-only memory, or kernel security check failure. So that triggered my attention because these are interesting messages. So it was actually kind of a memory corruption error. I was wondering what was going on and investigated. I narrowed down the case to a sequence of 2 out operations. One was a fixed one, the other one was the value could depend a bit, 2 bits needed to be set in a certain way. And it was because of a state machine, because it was getting into a precondition and then getting to a given function. And actually it was because of the legacy A20 device. And what was happening is that it was updating the host memory mapping, but the guest was keeping the same mapping, so everything was failing. And I was really wondering if it was possible to compromise VBS, and that's why I was interested in that one, virtualization-based security. What I was wondering was it possible to read some memory from the guest that it's not supposed to read? Well, it was kind of a roller coaster, but eventually, no, unfortunately, because the problem is that the VM is about to crash. We want to save some memory in that case to do that, which is not possible because it means writing to disk. Writing to disk is super slow. It requires access to memory. Well, there's a loophole here. It doesn't work. So had it been possible, not exploitable. So I shared it with MSRC. It's not a security bug. Although the good news is that it validated the behavior of the fuzzer. Crash handling, reproduction, everything worked like a charm, so good news on that. And also, it highlights that this surface has probably received plenty of attention already, and there's probably not much to be found anymore. So getting back to the future endeavors, there are 2 limitations for now, I would say. Space, because I restrict the fuzzer to the userland of the root partition. And as of today, this is not something I want to change in the future because in between some other tools were developed, like HAFR 1 and 2, which already fill the gap, bridge the gap. Time is a limitation that is a bit different and could be some things could be done to optimize that. So the future work will mostly be around that. First, developing the fuzzer internals. So in terms of speed, replacing debug shell by something else. For example, minimal debugger. Or also, in terms of speed, replacing some parts by C++ or C# to get more speed. Also on the execution and get rid of some of the scripting. Enhance the mutation strategy also by using existing engines. Not that the engines could be used as a whole, but at least use the logic. Porting to GCP Azure, get more runs. and adapting to other targets, so other devices, also port to other cases in userland, because right now we can consider that the tool is kind of a shell, and it's possible to modify some functions that are sent to the VM and some input handling, and it could be used for other cases. So as a conclusion, the instrumentation goal was reached. A Fuzzer was written. It is coverage guided. It covers the, some binaries in the userland of the root partition for Hyper-V. It's now open source, and contributors are very welcome to participate. The first version was published a few months ago. And it's still ongoing work with more runs expected and some more targets in the future. Well, thank you very much for your attention. And I will be around if you have any questions, or you can DM me as well. Yeah, thank you.